So our next speaker today is Dr. Mario Tenuta, who's the NSERC WGRF and Fertilizer Canada Industrial Research Chair in 4R Nutrient Stewardship and a Professor of Applied Soil Ecology at the University of Manitoba. His training includes a BSc in Botany and Physical Geography, an MSc in Soil Science, a PhD in Plant Science, and a postdoctoral research in nematology. The Industrial Research Chair program is advancing research in 4R nitrogen management practices on the prairies to give farmers and industry solutions to increase sustainability and soil and environmental health. So thank you for joining us today, Mario, and I'll turn it over to you.
Thanks, Anne. Okay, let's launch into this. I'm going to put a link in the chat. I just did right now. And you are also going to see a link on a screen. Can you see a screen that says My Organic Farm Is? Yes, great. So if everyone could go to www.menti.com on your phone, or if you have your fancy and have dual monitors and stuff, go for it. And use the code 89574876. And we're going to have about 12 questions. And the idea is to see, actually, it's to inform me and help me learn more about organic producers and your nutrient management or approaches and thinking. And it's also going to help me in the rest of the presentation because I'll probably draw on the points that we gleaned from it. So hopefully you're at the menti.com with the code there. Now I have to say the survey is completely anonymous. I have no clue who's answering. We're not tracking this at all, okay? So it's completely anonymous, okay? So, and how many people do we have? It looks like there's about 42-ish people with us.
Yeah, it says about 45.
Okay, good. So we'll probably wait till we get around the 35 mark. So this first question is basically about the size of your farm. Smallish, intermediate, and larger than a quarter section area. So the faster we input and answer the survey, the faster we roll along and don't have dead space, or we're forcing me to, sing a song or play ukulele for you or something like that. So 12 people, maybe people are still eating at the same time. Okay, this should be this will update as you roll in, so you can still roll in your answers. So this is great. So we have a nice mixture here of farm sizes, the large scale to the small scale, and because of the size, your considerations and your the attributes of your farm are going to be quite different, and your nutrient management approach will be quite different as well. So, oh, they're hidden. Okay, so we'll go to the next one now. And you raise for commercial sale vegetables, fruit, livestock and forage. Now you can, you should be able to put in multiple selections there, okay? If you have different, if you're diversified.
We're wondering what we put if we are grain farmers, or none of the above.
Oh my goodness, I forgot grain. Oh, that is a good question. Okay, we can manipulate that pretty easily. Remember, you can do multiple. Thanks for pointing that out. Am I missing anything else? Fish, snails? Let's wait till we get to 15. Maybe we won't wait till we get to 15. Okay, so heavily skewed to the grain side of things, and it probably coincides with those larger farms. And then there's livestock and a small amount of fruit and veggie. Okay, so good, that helps me. Organic production protects the environment from nutrient pollution. So compared to other means of producing food, it keeps nitrogen and phosphorus from getting into the environment. Okay, that was a little faster. Okay, a resounding yes. Okay. Good. I'm sure that's part of the reason why you're organic. Okay. My farm's sources of nitrogen are, again, you can pick multiple. Legume plowdown, legume intercropping, livestock manure, compost, other amendments, or rely on existing soil reserves. Wonderful. So we're using biological nitrogen fixation to bring that nitrogen in. Excellent. And manure and compost. Good. Your farm's sources of phosphorus are rock phosphate, animal manures, compost, struvite, other amendments. You rely on microbes and the soil biology, or you rely on existing phosphorus in soil. It's a spelling mistake. It's even in the title too. Oh my goodness. Phosphorus. Okay, now I suspect there's probably some combinations in here. Obviously there is, because it adds up more than 16. So there's a couple of different approaches relying here. Manures and compost, big, and then microbes and existing phosphorus in the soil. Okay. My farm is increasing its soil nitrogen content. So do you think that you are building a nitrogen reserve in soil? Great, some honest people. And okay, so you know, I see here that we're probably this is where we can probably use some help, I think. So let's see if we can talk a bit about that today. My farm is increasing its soil phosphorus content. No, yes, it's in balance. It means it's not increasing over time. And you don't have an opinion, never thought of it, don't know, all those kinds of things. Okay, we're on the no side here. And okay, good. So I think we are going to hit upon this and talk about phosphorus a lot today. That's good. I add nitrogen to soil based on, now we're getting a little fancy here with the questioning. You add nitrogen, however you add it, based on expected crop removal of nitrogen, soil testing, past experience, what's on hand, and possibly certifiable. So I would say if you're using plow downs, which are difficult to control, it probably is in the latter, or it could be past experience in terms of if it works for you. Really, the first two are more being very active with a pencil and paper and trying to figure out addition rates. Okay, great. So right across the board. Good. So we have a mixture here of approaches. And similar, how do you add phosphorus to soil? What you expect for crop removal, the soil testing, past experience, what's on hand, and what's available, certifiable to apply. Let's see if it's similar to nitrogen and being level across the board. Fairly level. Okay. Fairly level. Good. I don't know if this is statistically different, but what's on hand and certifiable. Sometimes obtaining good phosphorus sources can be a challenge, right? Wrong button. Soil test, your traditional soil test. Like if you were to send the soil off to AgVise or Farmer's Edge, do not measure what a plant can use in soil. And I haven't specified nitrogen or phosphorus here, just in general. Do you think they work, and are they useful in an organic system? In your system? And survey says, okay. So we are, I'd say, probably a bit skewed. Well, it's interesting. I was going to say skewed to agree with the statement, but it's yeah, well, it is, because it's agree. Neutral would be in the middle. So yeah, so most do not consider soil tests to be super relevant in terms of what the plant can actually utilize in soil. Now, do you test your compost or manure before using? All right, Vikram says yes. It's supposed to be anonymous, Vikram. Never, sometimes, always. Okay. So definitely skewed to not testing, or at least not consistently. When compost or manure is added, is it added at a specified amount in terms of knowing the weight added to soil? I guess if you use volume and you know the nutrient contents of the volume, that would be a rate. But the key is either weight or volume per area of land. Excellent. Okay, so then you have means to weigh. Great. Okay. Oh, no, we're going to come back to that one. All right. So you can still hear me, is that right?
Yes.
Yes.
Perfect. Okay. So it's always I always feel like I'm talking to my wall in front of me without seeing people there. Okay, so let's launch into it. For our nutrient management of organic crop production. Pleased to be here. And so this is a topic that I work a lot with in conventional systems. But when asked to speak here, I said, well, I wanted to push myself and said, well, let's think about organic production systems and the 4 R's. So this is just really the beginning for me and thought path. You're helping me out here. And we'll see how it goes. And I hope over time we'll refine it, because I do think the organic nitrogen nutrient management for organic systems we're lacking in that. We're not giving enough emphasis to these systems in support for research extension. So let's go back to 101 nitrogen cycle, where additions of nitrogen can be from biological fixation from those legumes that a lot of you are using, root decay, residues, manure. Some of these are additions to the field, such as biological fixation, or if you bring in compost or manure from outside, where the bedding and so forth has not come from your farm or your land area, then that's an addition. If it's roots and residues, we're talking about recycling. And if it's manure that from your farm, it's recycling as well. In some cases, there could be certain amendments, in this case, not fertilizers that I have here. But the ones that we're using more so in organic production will go into this pool here of our soil organic nitrogen, and then soil organic nitrogen that is then dependent to flow through using the soil biology, and then providing available forms, which then can be taken up by a crop's roots. And like I said, there's some recycling from the residues and the dead roots back into the organic matter. So we can have some cycling, and we can have the additions and new production. And this is for the nitrogen cycle. Now, this is going to be quite different than this when we get to the phosphorus cycle. And if we look at the losses of nitrogen in a field, they're given here in yellow, large yellow. And so we have crop removal. This is a loss of nitrogen if that crop isn't processed through an animal and then brought back to the soil as manure or compost. Even if it is brought back to manure or compost, we lose a portion of the nitrogen during that storage or the processing or composting. So we still have losses. Even if we think that we're recycling, we're not 100% effective in recycling. We're probably around 60% or so in terms of effective in the recycling with the manures and compost. And that's just a really rough estimate there. We have other losses as well, erosion and runoff, which in some soils can be very important in some years, because this material that moves off is very light and fluffy and contains a lot of organic matter, which contains a lot of this soil organic nitrogen in the soil humus and organic forms. If we have nitrate left over from a crop, or if it builds up and the crop there's no active crop taking up the nitrate, and it's wet conditions, and we have a soil that isn't like the Red River Valley with clay, then we could have leaching losses through percolation of water down the profile. And that can be important in soils that are on lighter textured soils. And then we can have gaseous losses, ammonia, and also nitrogen gas and this greenhouse gas here, N2O, being emitted as losses. So nitrogen is interesting in that there's a lot of pathways to lose, and it can be created through biological nitrogen fixation. That is way different than phosphorus. Phosphorus is a completely different beast. So we can add phosphorus to soils as amendments in crop residues. So that's recycling the crop residues there, or amendments, compost if it's not recycled, if it's bringing in compost, meat and bone meal, for example. Bone meal, that would be bringing it in, struvite, bringing it in to the farm, applying it to the soil, and it can go in several directions. And this is a problem in terms for phosphorus, in that some of it can go into a pool that plants can readily take up. So it's dissolved in water. Not much of it goes here. A lot of it goes into the mineral P fraction. So in other words, it creates new minerals or rocks in the soil from the addition of the phosphorus. And then some can be taken up by microbes into their biomass. So it's a reservoir of microbial phosphorus. And then some goes into organic matter in terms of phosphorus. And you can see the arrows, there's lots of connections between the boxes and arrows, right? So there's exchanges happening here. This is a really tough one here, where this good stuff here that plants can use gets converted over to inert phosphorus. It gets socked away into rocks and minerals that are not usable. So a good portion of our phosphorus that we add as fertilizers ends up in here, okay? All these other pools, like we call these pools or compartments or reservoirs of phosphorus, are available to plants. We're going to talk about arbuscular mycorrhizal fungi that can provide phosphorus directly. These fungi can solubilize mineral P. I should have put an arrow right in here, mineralize P, and take it up and then pass it over to the plant. We can have mineralization of phosphorus from soil enzymes to convert organic P into soluble pool. So there's quite a few dynamics here that's happening with phosphorus. But notice what's really missing here is that we're not creating phosphorus anymore. We're not creating it. We're not making the element phosphorus like we are with nitrogen or ammonium, organic nitrogen with fixation, biological nitrogen fixation through legumes. So that's the thing about phosphorus, is that if we do not add phosphorus, then we're completely dependent on the internal workings of the existing phosphorus that's in that soil, okay? And sometimes, and a lot of times, we try to rely on the microbes and to help tap into that phosphorus. And they can do that. However, they will have a challenge if the phosphorus levels are so low. And we'll talk about that, and we're going to show that, okay? The other major loss component is this crop removal here, where we take it off as grain or feed and vegetables and so forth. So that's important, because that's the phosphorus is gone. So over time, with more crop removal, we can deplete the phosphorus if it's not replenished. So this brings us to approaches to nutrient management, okay? And so we have three approaches. There is draw on the soil reserves without replenishing them. And I'm calling that the minor, okay, the minor. Another approach is to build fertility and then just replace what is lost. So you kind of get a good level and then just keep it there and keep track of your removals and maintain the levels by replacing the nutrients by adding them back to soil. That's the maintainer. And then the third approach, which let's call it the nurturer. And that is to rely on healthy soil to provide nutrients. In other words, promote soil health, get those soil organisms, their activity up, and have them release and provide the nutrients, nitrogen and phosphorus, to the crop. So we're still not talking about replacing at all here. We're just relying on the soil health of the system, okay? And so, yeah, so we have a question here. I don't mind stopping. What is the mechanism by which available P is converted to inert P? Okay, here, it's chemistry. It's pH and the presence of cations like calcium, magnesium, iron, aluminum, which can be, well, iron, aluminum present, calcium, magnesium. So depending on the pH of the soil, we can have often lots of calcium and magnesium, especially because from the carbonate, and that will drive to mineral P and inert P. In other words, we're creating rock, phosphorus rock. And to tell you the truth, the phosphorus is really going back to where it came from. It's really going back to where it came from, which would have been in this rock form. Okay. And notice it can go directly from here to this inert P, but this inert P generally doesn't go straight back to inorganic P. It generally has to go to other mineral forms that can then become slowly released. It's a slow process going back, but it's a fast process going that direction. Okay. That good, Will? Okay, so soils can naturally provide nutrients. Yes, they can. They have reservoirs in soil as in microorganisms, so I would call that microbial nitrogen, microbial phosphorus, in organic matter, so organic matter and humus, and in minerals in the soil. This pertains to the phosphorus. So there are reservoirs in there. The matter is tapping into them, and also to ensure that they can supply nutrients to the plant. The nitrogen is in microorganisms, organic matter, and can be created. So we talked about that. It's different than the others, and phosphorus, calcium, and so forth. It's quite different in that those cannot be created. Okay, they're not created. They're what's there in the soil is there, or what we add to the soil. Okay, so we're stuck with what we got unless we add it back. So it's a big difference. It's a different approach. So when you're thinking about nitrogen, different mindset than phosphorus management. Okay. Here's an example. The Glen Lee long-term crop rotation and management study, headed up by Dr. Martin Entz in plant science at the University of Manitoba. We've done a lot of collaborations here. We had a collaboration with a graduate student. And we looked at, with the student, Kathy, looked at the balance of phosphorus in the rotation of conventional and organic production, and then with different rotations of grain only, which is the annual, inclusion of perennials phase to your alfalfa phase with the annual. So that really should read perennial plus annual. This is perennial phase. And then there's that perennial with annuals with compost and conventional or organic. And the bottom line here is this kilograms of phosphorus per hectare. This is after 14 years. How much phosphorus was added more than removed by a crop, by the crops grown there. This is as follows. In the conventional systems, they're all positive. That means more phosphorus was added than was removed. So there's a chance that phosphorus was building over these 14 years. In the organic system, it's a way different situation. In the organic systems, in all cases, they were drawing down phosphorus. There was a deficit of phosphorus and losing phosphorus. And the loss was the greatest where there was an inclusion of the alfalfa in the rotation. And you know why. Alfalfa is very productive, right? You get multiple cuts and it's being removed. In this case here, there was no addition back of manures from the alfalfa, and there was a deficit as a result. Now, Martin realized, and I'll show you why, why he added them compost as a strategy to start to replenish and restore. You can kind of think of it as, in effect, recycling some of that phosphorus back to the land. Only one phosphorus addition was provided when we did this 14-year determination. And you can see it started to bring down the balance. So over time, and Martin has done this, that every 3 or 4 years, adding compost, and it's cattle compost, cattle manure compost, it's starting to replenish the soil reservoir of the phosphorus. This is the impact, in effect, of this system, the organic system, which is really a mining strategy for phosphorus. In that you can see the impact on the yields, and where there was building phosphorus, the yields are much higher in the conventional system, and where there was a mining of phosphorus, there was a decrease. Okay. Interestingly, in the perennial annual rotation, there's a good amount of nitrogen coming in from the alfalfa, but you see a little bit of a yield increase here, but it's really heavily deficient because of phosphorus. So you're not seeing what it really can do because it's limited by phosphorus. It's got the nitrogen, it's limited by the phosphorus. And you can see just even that one-time addition of a small amount of cattle compost boosted up the yields. Okay. So it's really dramatic impact here of relying on the soil over time isn't a great strategy here. It needs to be replenished, okay? Because even building soil health and microbes, and I'm going to show you this in a moment, is not enough to overcome severe deficiency of nutrients. Even the microbes out there were deficient of phosphorus. This brings us to the 4 R's. You're probably wondering, when the heck is he going to talk about 4 R's? What are these 4 R's? Well, for fertilizers, we talk about 4 R's as a framework to help a farmer come up with the best available decision for today or at that moment with available resources on hand and weather conditions and so forth. It's the right rate of nutrient addition, choosing the source of the, in this case for conventional folks, fertilizers, where to put it at the surface, Broadcast Incorporated, Bandit, and so forth, and when to apply it, fall versus spring, early fall, late fall, a bit up front at planting, a little bit more split application in season. So in this case, we're dealing with fertilizers. And I tell you, that simplifies things compared to organic systems, of course. It boxes nicely into these categories here, but we're going to think you know, we want to challenge ourselves, and we're going to think more in the organic realm. So let's first talk about how much to add. Here is an estimate of the typical crop removals of nitrogen and phosphorus from field crops, okay? And I'm thinking that those yields are fairly realistic for organic production. And you can see that there's nitrogen and there's phosphorus. The phosphorus is as P2O5, which is standard representation of phosphorus. It's not like that in soil. It's not in that form in soil, but it's a legacy thing that because of history, we're kind of stuck to showing it like that. These are the pounds per acre removed in the crop, not what's recycled, you know, it doesn't include what's recycled, it's what's coming off in the grain, okay? And so you can see anywhere from 45 to 76 pounds of N, and anywhere from 14 to 33 pounds of phos in the grain. Now, we look at vegetable crops. Now, a few of you are vegetable crops. I was expecting to have more vegetable people, so I worked really hard to get this table to show you. But anyway, you can see it's quite a different story of vegetable crops. Generally, the nitrogen removal is a lot less, except for beans, legumes, where there's a lot of high protein, and of course they're fixing a portion of their nitrogen. And the phos is generally lower than for the field crops. And continue with the vegetable. I told you I worked hard generating the table for you. And then you see it's quite a bit of variability. Some crops are surprisingly higher phosphorus removers for vegetables, and some are really pathetic, like radish. And so the first thing that strikes me is the variability here, in that if you have some of these crops that are very prominent in your rotation, then they're going to either cause a lot or a little removal, okay? We have a question here. Let me just take a pause here. In the Glenlee study, they tried to do 2 cuts if possible, okay? Not every year was possible, but definitely 2 years. I think even Martin might have boasted about getting 3 cuts in some years too. The whole P cycle is needing attention. Doing better with our P would make more jobs and not waste as much food. Food should be respected. Yeah. Yes, we're going to talk a bit about this. And there's a good poster on recycling from Joanne Thiessen-Martins on struvite later in the day too. Okay, so now let's switch to forages. Look at the nitrogen and phos removal with forages. So this is in terms of taking it off, mechanically harvesting. That's hay. The alfalfa, very high on the phos for removal, 62 pounds, and high on the nitrogen for removal, but it fixes its own nitrogen, so that's not a real big issue, right? That's not a big problem. Grasses, high on the phosphorus removal, fairly high on the nitrogen removal, so forage grasses. And clovers, not so much on the phosphorus, but fairly high on the nitrogen if you can get a good yield of the various clovers. So this is a key thing, and this is what was happening at Glenlee. The alfalfa was removing a lot of phosphorus when it was in the rotation, and in the organic system, this removal was deadly in drawing down the phosphorus levels and making the system deficient, and then impacting the other crops, is not only alfalfa, but the rotation grain crops, okay? So keep in mind, if you have alfalfa, and many of you have livestock, so I suspect you do have alfalfa and legumes in a forage. It might be a mix with grass, so you can kind of go intermediate here. So it's important that this is something we need to be very well aware of and manage and watch out for our soils. Now, biology comes into play here, and Kathy also looked at vascular mycorrhizal fungi. So there's arbuscular mycorrhizal fungi, or AMF, on the top left in flax. And these are flax portion of the root. And you can see the individual cells of the root cortex. And here's the running hyphae of the AMF. And here are the arbuscules. There's penetration into the cell wall. And then that arbuscule, this cloudy thing here, is where phosphorus is given up by the fungus to the plant cell, and the plant cell provides food, energy to the fungus. This lasts for a few days, and then the fungus disappears and goes to another cell and does the exchange. Okay, and by the end of the season, every cell in the root has had this exchange, been able to pick up phosphorus. Okay, so that phosphorus then can then be loaded up into the phloem, the vessels in the that go to the leaves, and moving up, bringing the phosphorus to the rest of the plant. It's a good thing, right? Now, these fungi, I should have put a cartoon in here, they're utilizing some of that mineral P, okay? Solubilizing that mineral P, taking it into their hyphae, the hyphae go through the soil and then go into the root, pass on the phosphorus, okay? So it's a helper. And Kathy was able to look at signs of the children or the progeny, which are spores of the mycorrhizal fungi. And the first thing you can see is what? A hell of a lot more spores, right? With the organic system, huh? Tons more than in the conventional system. Is there more in the grain only versus forage grain compost? Not that I can't really see it here, but there is a difference in the communities. So the shape and the color of those spores really are different species. And the mycorrhiza are quite different, okay, between the grain only organic, and then in the diamond here, conventional forage grain, organic forage grain. So there's separation between organic and conventional here. And then the triangle here, conventional grain only versus organic grain only. Quite a separation here. So the communities have started to evolve after only 14 years. And it's because of the phosphorus, okay? Because of the phosphorus levels that are changed. So the microbes are really trying to help out the plants here, okay? But we saw that the levels of phosphorus were so low that the yields were still impacted, okay? So even the microbes are trying to help, still not able to get over just a really severe deficiency, okay? And let's look in the roots. Kathy, this would have been for the flax, I believe, and the root colonization with arbuscules, much higher in the organic system compared to the conventional. So they were helping out, they were trying to help, but even them couldn't overcome the phosphorus deficiency because of the lack of replacement of phosphorus and the removal, the crop removal. All right, let's move now to, well, how are we doing Anne for time here? I don't have a watch in front of me.
About 15 minutes left.
Alrighty. Okay, I need to move because I want to give you a chance to ask some questions. So nitrogen and phosphorus contents of typical amendments. So we've looked at removals. Now let's look at additions that we can bring back in. And I've tried to put this in terms of pounds of nitrogen or phos per ton. That's imperial ton, 2,000 pounds of the material as is. So not dried, but as is, as you would have it on your farm. Okay. The first thing you can see is solid beef manure is fairly low in nitrogen and fairly low in phos. Something like solid poultry manure, it's just jacked for nitrogen and phosphate, just massively jacked. So this material is going to behave way different than beef manure, and I think you know that, right? Sometimes we refer to poultry manure as being hot, right? Because it can burn the crop because there's too much nitrogen. Now, if we compost the material, look what happens. We compost this beef manure, we actually get less nitrogen. Weird. Well, it's because we're losing nitrogen to the atmosphere during the composting process. But it's concentrating the phosphorus. Remember now, we've lost material. If you've composted, you know their pile shrinks by like 2/3 almost. You're concentrating the phosphorus. And so that's what's happening here. So we actually create an amendment that's got a really good phosphorus content to it, okay? It's not great on the nitrogen side as an amendment, but it's great on the phosphorus side. So we need to be careful with that when we're using compost and even yard compost. So this would be using plant material. You could have this on your farm in terms of vegetable producers would have lots of refuse and material that they would compost from what they don't sell off to market. But this is actually for the city of Winnipeg, so it has lots of yard clippings, a lot of grass in it and stuff like that. And the phos is okay, not as high as the manure, but has a lot more nitrogen, and it has more nitrogen because of those grass clippings and stuff from the kitchen that's in there. Less phosphorus because we just the feed what animals eat, and they don't need that much phosphorus. It just gets thrown into the manure and gets concentrated in manure and then concentrated in the compost. And well, we're not putting that much phosphorus to begin with. The materials going in as raw products for yard compost doesn't have as much phosphorus. So if you're using compost, think about it. Is it animal manure compost or is it yard compost? Okay, they're going to be different for the amounts of the phosphorus content in them. Okay. Now let's look at some other amendments that some of you may use. It's going to be really expensive on a large scale. Blood meal, jacked in nitrogen, decent in phosphorus. Fish products, look at the fish products. High in nitrogen, high in phosphorus because of all those fish bones. And meat and bone meal, similar thing. There's protein, so we got from the meat rendering process, decent nitrogen and very, very high phosphorus from the bones. Okay, very good source of nitrogen and okay for good for nitrogen as well. If we go to struvite, so this is the recycling that Joanne is going to talk to you about, and I think Laura is saying also Michelle. Kartner was well later in the day. Some nitrogen, decent amount of nitrogen. I mean, this is pounds per 2,000 pounds of material, and very high in phos. Okay, very high in phos. So it's a very good candidate as a phosphorus amendment, and it's potentially certifiable as well. So there's different choices here for you. And some are going to be good for nitrogen and some are going to be good for phosphorus. Very few of them are good for both. Okay, so it complicates things for you a bit more. Now let's look at balance. And what I'm doing here is saying, okay, let's apply these amendments, an alfalfa plowdown, a grass plowdown, fish meal or yard compost, yard trimming compost, and apply them at a nitrogen removal rate of the crop. In other words, satisfy what the crop is going to remove for nitrogen. So with alfalfa, it's challenging to fix the rate, obviously. So we grow some alfalfa. It's probably after a second cut, let it grow a bit, and then we plow it in late summer, early fall to decompose. And I've given an estimate of how much nitrogen that can provide, that strategy. So we use at Glenlee. In that case, the alfalfa has phosphorus in it, but what we're adding there is still less phosphorus than the removal of barley that would have been grown the following year. It meets the flax and lettuce requirements, we grew those, and doesn't meet the potato requirements in terms of what's harvested there. It's quite a deficit in terms of pounds per acre phos decrease. This should be P2O5. This is not P, only phos, okay? But look at the nitrogen. That alfalfa plowdown actually met the barley and potato needs, but it was excess for flax and lettuce. So they don't draw as much nitrogen off as potato and barley. So it's a little challenging with alfalfa to get it perfect, because you're not adding it at a rate. You get what you can grow and that regrowth and plow it in. Grass plow down, a little different, definitely not as much nitrogen present from the grass plow down, and the phosphorus as well. It's a similar story for phosphorus for barley and potato being quite deficient, and generally deficient for all crops for the nitrogen. Now, if we look at fish meal, remember we're adding it at the nitrogen rate. So the nitrogen amount of fish meal to meet the nitrogen requirements for removal of these crops. Excess P right across the board. And if we do that yard compost to meet the nitrogen removal of these crops, look at the excess P. Astronomical. Astronomical. Okay. So we have to be careful. If you're relying on some of these products for your sole nitrogen requirements for your crop, you could run into the issue of massively building phosphorus. Now let's look at P removal rates. So addition of, and I kept alfalfa the same because it's common in organic systems. I've added poultry, solid poultry, beef manure compost, and meat and bone meal. And in this case here, the alfalfa, well, so these are the same numbers you saw before. But now with the solid poultry, in this case, we're adding for the phosphorus removal, but there's deficit of nitrogen with the poultry. Okay. The beef compost, deficit of nitrogen. And meat and bone meal, deficit of nitrogen. It's because the nitrogen requirements are so much more than the phosphorus. And those products are very high in phosphorus, so we don't have to add very much. And so there's just a deficit. Okay. So be careful here, and this is where probably mixing and matching is good in terms of a combination of that supplies the nitrogen and supplies the phosphorus and add them together. So this is Glen Lee, pictures from Martin. And so here is flax with some weeds and no, it's not flax. Then no compost over here, and then there's compost over here. And you can see just more productivity here, a bit more weed growth too, but more productivity here. Okay, with that compost, really boosting the productivity. And here's with the alfalfa, big dramatic difference in the alfalfa with compost added, beef manure compost, because he's replenished now and started to go into and become a maintainer of phosphorus. And this just shows you once with the continuous adding the phosphorus, the compost, the yields, this is without straight organic, without replenishing the P, and this is replenishing P, and it's able to build up and get pretty decent yields with the organic system, okay, at Glen Lee. Now, talk to you about some of these amendments like compost that have high phosphorus can be problematic if we're adding them to soil, especially for our nitrogen requirements. I had a student, Stephanie Daly, and she looked at garden soils. I know there's not organic systems, but sometimes people think they're kind of like organic growers when they produce vegetables, okay? They don't add fertilizer and stuff like that. And they have compost, you know, they're gardeners, they're gonna compost too. And but let's look at the levels. She looked at the levels of phosphorus in garden soils that we were able to get. We asked volunteers to bring us soil. These are all university staff people. And these are the ppms. And you can see it about centered around 70, 75, but there's a lot of high ones. In 2004, we did the same thing with new soils. And again, some around 75 and some few highs. We got data from AgVice for commercial grain farms, vegetable farms, commercial vegetable farms, because we were thinking they grow vegetables in gardens. And you can see a lot lower Okay, so the folks that are thinking they're doing really awesome gardening and so forth like that are really jacking their soil in phosphorus. Okay, and why are they doing that? Or sorry, how are they doing that? It's because they're adding compost every year, and they shouldn't be. Is Karen telling me to wrap it up?
That'd be great. We got some questions, so feel free.
Yeah.
Okay, let's do that because I'm just going on and on here, and so let's open it to discussion. I think you get the message here. What I'm talking about, the rest here is really backing up this idea of the nitrogen, phosphorus, and the amendments of being careful. Okay, do you want to lead us through, Karen?
I can ask a few questions here.
Brian?
So the first one that I see here is, would I be correct in assuming that supplementing cattle on pasture with grain would increase P accumulation?
Supplementing cattle on pasture with grain increase P accumulation. Well, yes, because the cattle do not take up that much phosphorus to build up in terms of bones. If you like, especially like if you're backgrounding or if this is breeding stock, cow calf with the cows. Yeah, so a lot of that phosphorus will go onto in the paddies, and it doesn't volatilize, doesn't get lost, microbial breakdown like nitrogen does, and it will go back to the soil eventually. So it can increase over time, especially if that grain is from a different land,
Thanks. The next question here is, under which conditions do the mycorrhizal additives not work? I think they're talking about the mycorrhizal additives promoted by various companies.
Okay, so inoculum. So that's tricky because a Brussika mycorrhiza really won't help us if we have high phosphorus levels in soil, if we till soil a lot as well. Okay, they're not going to help us too much. So we need soil, first of all, that isn't very much tilled. And then secondly, that doesn't have high phosphorus. But if it has very low phosphorus, the inoculants won't help either. So I always think of it as we need a sweet spot of phosphorus levels in the soil. Okay, kind of intermediate. If you want an Olsen P level, I'll tell you, it's, I would probably say about 12 to 15 ppm Olsen P as a sweet spot. Now, will the inoculum work or not? The best inoculum is the stuff in the soil, and it's the fungi that grew last year, and they're still there as hyphae, and the roots coming from a germinating seed encounter those hyphae, and they get colonized very quickly. If you add the inoculum, it comes in as a spore, and that has to be activated by roots to germinate, and then grow to the roots, become colonized. It's a little bit slower than the natural inoculum in the soil. So if you can reduce that tillage. Now, the other thing is be careful with, like, if you have something like canola, and then you're following it with a high mycorrhizal loving crop like corn or flax, and you have low or intermediate phosphorus, Olsen P, you're going to have a problem with the flax and the corn. Okay, and so I know that there have been some marketing pushed towards those kinds of scenarios. I would say use your crop rotation wisely to just go into a cereal instead, following that canola.
Thanks, Mario. Definitely the more cost-effective approach as well. The next question is, what are the ways that we can assist the microbes in plants in assessing the phosphorus from the soil? So Scott's referring to your nurturer approach.
Okay, Scott. Yeah, so tillage is one. Reduce that tillage. And it doesn't have to be completely no-till. It might be just in terms of shallow till. In some cases, it might be even strip tillage, or just don't till the whole thing, and don't do it aggressively. Because it'll break up that I call it a hyphal highway network. Okay, we want that to be intact, and it doesn't get broken up because of winter. So keep it intact. The other is don't super load your phosphorus levels. Don't have them depleted like we did at Glenlee for the first bit. Keep them in that intermediate sweet spot, and then have reduced tillage if possible. It can be challenging in organic systems, and also choose your rotations wisely. If you have a crop that is non-mycorrhizal like canola, then be careful what you follow it with. Don't do a sunflower, corn, or flax, which really like mycorrhizal.
And then we have another, I guess, yeah, another question here is, I'm not sure if you answered this or not, but what is the mechanism by which available phosphorus is converted into inert phosphorus? And this is in reference to one of your early on slides with the phosphorus cycle.
Yeah, so we mentioned before about it turns into a rock, into minerals, and it usually gets tied up with calcium, magnesium, iron, and aluminum. Iron and aluminum are the worst. Those are really tied up and forever. Forever, you just really impossible to get that out unless you add a strong acid and dissolve it, and that's not going to happen in soil. So it's working against us. Nature's kind of working against us. You know, I could tell students, my students, that mycorrhizal association was invented to allow plants to live on soil, live in soil, to become terrestrial, because phosphorus is just limiting in soils, period. And in agriculture, we've used fertilizers to increase it and get that productivity up. In organic systems, we have to think about, we still have to rely on additions of phosphorus. And we can nurture the organisms as much as we can. We just talked about that. But we do have this thing working against us in terms of going to inert forms. I don't know how, in terms of organic systems, in terms of, like we did, Kathy looked at the inert phosphorus and couldn't find a difference between the organic systems and the conventional systems. They're all high. Like almost 50% of the phosphorus is inert phosphorus in soil. In other words, plants can not get at it and probably will never get at it in our lifetime and your children's lifetime. So yeah, I'd have to go into a lot of chemistry to get in that nitty gritty. Okay, but just say, put it this way, nature is kind of working against us, and it could be related also because of our soil pH and the cations that we have in the soil.
Great, thank you. I think this was a very informative presentation, and yeah, I personally, learned a lot, and it's good to have a refresher on, like even the phosphorus and nitrogen cycles, because it's very relevant for anyone that's farming and thinking about those things.